Hey, how are you? Welcome to my demo lesson on sketching rational functions. Now, this is one of the topics that shows up in pre-calculus that most students tend to struggle with. So as a result, today we're going to actually go through the process of actually sketching one of these functions. And this one is so much of a beast, it's so much of a large problem. So it's going to take us a little bit of time to go through the process. So I want to introduce myself. I'm Dwight Dunn. I'm presently a teacher at Cleveland Community College and also an instructor with Charlotte Mecklenburg Schools where I teach IB Math and AP Calculus. All right. Also, that's my website because I do offer free tutoring for mathematics for varying courses. So you can check me out at www.dun-s-tutoring.com. All right. So let's take this problem first. Now, you may be asking right here, why do I write this problem two ways? Notice I write with the bottom being factored, and I also write with the bottom without factored right here. And the reason for this is because depending on what we're trying to find, depending on what type of asymptote, it's pretty important to use both forms, and that can tell us different things within the process. So let's go through the process now that is required to sketch a graph of this magnitude. So the first thing we're going to look at is what is called the VA, or the vertical asymptotes. Now again, if we recall, an asymptote is normally a line, in this case, where the graph is approaching and it gets infinitesimally close or very, very close to that line, but it never ever touches that line. So with that being the case, let's look at this now. So for the vertical asymptote, what we're going to do, we want to figure out what value of x will make this function undefined. And as a result, to identify where it's undefined, we simply need to equate the factors in the denominator to be 0. So that's going to be 2x minus 1 equal to 0. And that's going to be x equal to 3. So it's x plus 3 equal to 0. So with that being the case, we have now 2x, which is going to be equal to 1, divided by 2, divided by 2. I'm going to get x equal to a half, and I'm going to get x equal to negative 3. So these two here represents my vertical asymptote. Now if I may digress a bit, notice that what these vertical asymptote didn't factor out in the top, right? So as a result, we know for sure they are vertical asymptotes. If for possible, suppose for instance this function have x plus 3 in the top, and this cross out like that, if we have something in the top like that, x equal to negative 3 wouldn't be a vertical asymptote, but would actually be a hole in the graph. So I just want to be clear with that. So the hole in the graph is identified by common factors in the top and the bottom, while the vertical asymptotes are identified by simply equating the bottom to be equal to 0, and they don't factor into the top and the bottom. All right. So that's the case for that right there real quick. So that's our vertical asymptote. So we're going to call this step 1, and we're going to break these down now into different steps. So if we keep it going, the next thing I'm going to find out now is the horizontal asymptote. So to find the horizontal asymptote now, it's easier to work in this format. And to work in that format, what I'm simply going to do, I am going to divide by the highest degree of x. So I'm going to have x plus 1 divided by 2x squared plus 5x minus 3. If I divide now, let's change up the color a little bit. I can use something pretty cool. Let's use a different color. If I divide by x squared, 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 I realize my result will yield 1 over x plus 1 over x squared divided by 2 plus 1 over x minus 3 over x squared. Now, once we do this is kind of a routine that we're going to follow to find a horizontal asymptote. What we realize now is that we can actually take x tends to infinity and see what happens with these values. So let's check. So as x tends to infinity, obviously this value here going to approach 0. And the reason why this value is approaching 0 is because the bottom is getting extremely large as we approach infinity, and the top remain fixed. So it's like if we have a fraction 1 over 4, 1 over 8, 1 over 10, the fraction is getting progressively smaller. And if the top remain fixed, obviously the value that we're going to be approaching right there is 0. So this is going to be approaching 0. The same thing going to hold true for this one. That's going to be approaching 0. This will be approaching 0 as x tends to positive infinity, and this also would be approaching 0. So as a result, what I have remaining is going to be equals 0 divided by 2. So my horizontal asymptote simply going to be y equal to 0, or in this case it's going to be the x-axis. So this is my horizontal asymptote. So that's the situation there to identify the vertical asymptote and the horizontal asymptote. So for here, we're going to break a little bit more, and now we're going to look at how to identify the specific intercepts. So let's recap real quick. The first thing we want to emphasize there is that we find the vertical asymptote by equating the denominator to be equal to 0, right? And we find the horizontal asymptote by dividing by the highest degree of x and see what happens as x get very large beyond bound. That's x approaching infinity. So that's step 1 and that's step 2. All right, now let's look at step 3. For step 3 now, what we're going to determine is the y-intercept. So to find the y-intercept, what we need to do, we have this as our original function. So we have x plus 1 as our original function. Let's go back real quick. X plus 1 divided by 2x squared plus 5x minus 3. So if we have x plus 1, 2x squared plus 5x minus 3, and I need the x-intercept, all I simply need to do is let y-intercept, that is, my correction, all I need to do is let x to be equal to 0. Now if x is equal to 0, I realize that I'm going to get 0 plus 1 divided by 0 plus 0 minus 3, and as a result I'm going to get negative a third. So my y-intercept then going to be 0 negative a third, and that's my y-intercept. Also in the same breath, I need to determine the x-intercept. So for step 4, we need the x-intercept. So to get the x-intercept, what we're simply going to do now, we're going to let the y equal to 0. So we're going to have x plus 1 over 2x, because remember this was f of x, equal to that. So 2x squared plus 5x minus 3. So that's going to be my x-intercept. So to determine my x-intercept, I'm going to let y, because f of x represents y, equal to 0. Once that I equal to 0, I cross multiply. So my result here going to be x plus 1 equal to 0, because that's the only thing remain. And as a result, we have x equal to negative 1. So my x-intercept will be negative 1 and 0. So that represents my x-intercept. All right. So just a quick recap. So for 1, notice we actually determine the vertical asymptote. Then we determine the horizontal asymptote by dividing by the highest degree of x. Then for step 3, we find the y-intercept by plugging x to be equal to 0. Then step 4, we find the x-intercept by plugging y to be equal to 0. Now let's look at the next step, for number 5. So for number 5 now, we want to determine the intersection now of the non-vertical asymptote. So make a little note right here real quick. The graph can, so the note here is that the graph can intersect the non-vertical vertical asymptotes. Asymptote. So the graph can intersect the non-vertical asymptote. Now it sounds very counterintuitive, but the fact of the matter is, once you are not, the function is not undefined at a particular point, we still can have that value existing for the asymptote. So the graph can intersect the non-vertical asymptote. So to figure out if it intersects the non-vertical asymptote, what we normally do is set the graph equal to the non-vertical asymptote. And the non-vertical asymptote, if we back up real quick, is the horizontal asymptote, which we identify to be 0. So the non-vertical asymptote would actually be y equal to 0. That would be my equation, which is the horizontal asymptote. And as a result, if I actually set the function again, x plus 1 over 2x squared plus 5x minus 3, my result here going to yield the same as above. So notice right here, because I already determined the horizontal asymptote, the intersection of the non-vertical asymptote will going to yield the same result. So the graph, the key things, let's just do a quick review again. So we identify the vertical asymptote, we identify the horizontal asymptote, we identify the y-intercept, we identify the x-intercept, right? We then realize that the graph intersect is going to be the horizontal asymptote right here if we actually figure out where the graph intersect the non-vertical asymptote. So we're in a good position now to actually do the sketch. Now to do the sketch, we want to figure out at every point on the x-axis that a graph will have some critical thing going on right there. So the first one we want to look at is the vertical asymptote, which is going to be -3 a half. We also need the x-intercept. So let me go a little bit above this. So the x-intercept going to be -0.5, and we have, sorry, the vertical asymptote was -0.5, and if we back up real quick, it's going to be -0.5, +0.5 and -3. So that's +0.5 and -3, and we know that the x-intercept going to simply be -1. So if we have those things now, this is going to divide the x-axis into in important intervals. So we recognize for the first piece, we're going to have the first interval right here, which is going to be -∞ to -3. The second piece is going to be -3 to -1. The next piece is going to be -1 to a half. And the next piece going to be a half to +∞. All right, now looking at those intervals, these are the intervals we identify right there. Now notice here I select a test point. It's not very important what value you select, as long as the value exists within the interval. The only thing that we want to figure out right here, we want to figure out if the graph is below or above the x-axis. That is why we're going to pick values within these intervals. So if we pick -4, plug this into the original expression, which is up here, we realize the value going to be -1/3, suggesting that it's going to be negative, so it's going to be below the x-axis. If we select -2, we realize that if we plug this into this function right here and work it out, we're going to get 1/5, so that's going to be positive. Plug 0 in, the result going to be -1/3, which is going to be negative, which is below. Plug 2 in, we realize that the function is going to be positive, so that's going to be above. So for these different intervals, we recognize a number of different things. We're going to have below, above, below, above. All right, so let's do our sketch now. So to make a rough sketch, the first thing we're going to do now is put our vertical asymptotes in. The vertical asymptote that we identify was -3 and a half. The y-intercept we identified before was given to be -1/3. So we put that in. The x-intercept now going to be -1. So for the vertical asymptotes, we draw, put some dotted lines coming down. And then we're going to look now at the different intervals. We also know, we also know that the y-axis, the x-axis right here, going to be the horizontal asymptote. So if we have that being the case now, we know from negative infinity to negative 3, the graph is below the x-axis. So if it's below the x-axis, if this is an asymptote, this is an asymptote, the graph must be looking like that because it's below the x-axis. It cannot be above or approaching above because we know for sure that the graph must approach this asymptote, which is the x-axis, and this vertical line. Between now negative 3 and negative 1, we realize that it's supposed to be above. So this is the asymptote. We know it's intersecting this. So we know it's going to be facing this asymptote like that. And it's going to be coming like this, going through this point, of course. And that is negative 1 to negative a half. We know it's going to be below. So it's going all the way below. This is also an asymptote. So the graph must be coming down like that. So notice now we have those two pieces. For the last piece, we know from a half to positive infinity, going to be above. So it must be above the x-axis. So it's going to be over here. So that represents my graph. So this is how we go through and sketch a rational graph. This is a very, very tough problem. So we take our time and we break these down into multiple steps. So let's do a quick review of what we did. So this was my original graph, this was my original equation, which is equal to that. I firstly found the vertical asymptote by equating the denominator to be equal to 0. I divide by the highest degree of x to determine the horizontal asymptote. And I take the limit as x tends to positive infinity. Each of these approach 0, and I have 0 divided by 2 for my result there. Once I have that determined, because this is 0, this suggests that y equals 0 is the horizontal asymptote. For number 3, I then found the y-intercept by making x be equal to 0. I get negative a third. For number 4, I find the x-intercept. And finding the x-intercept, I let y equal to 0 and solve. I get x equal to negative 1, right? And then for 5, I test if the graph intersect the non-vertical asymptote, which I recognize by letting this to be equal to 0, which suggests that the value up there is the same. And then after that, what we simply did is break the intervals according to the x-intercept and also the vertical asymptotes. And then from there, we divide this into different intervals accordingly, do a test of each interval if it's positive or negative, and then after that, we then made our sketch. So that's complete our demonstration. Very tough problem, but I hope you enjoy this lesson.